Today we're going to talk about the median of a triangle and all of its properties and what it could tell us about other things about a triangle. So first, let's look at what a median is. So we know that a median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. We have a triangle A, B, C, and also what we have in this triangle is we have a point M. As we see on either side of M, we have congruent segments, and so we could say that M is the midpoint of segment CM. Okay, so what does that mean in regards to a median? A median is a segment whose endpoints are a vertex. We'll look at a vertex A. So we could draw a segment whose end is at A, okay, and the midpoint of the opposite side. Well, CB is the opposite side with the midpoint of M. And so we could say a median would be this segment as I just drew, because it's on a vertex and the midpoint of the opposite side. And so as I just said, we would call this a median. There's not only one median of a triangle, there are three medians, one from each vertex. And another thing to know is that it will always be inside of the triangle. Now we have a new word called the centroid of a triangle. The centroid is the point of concurrency of the three medians of a triangle. Just as a reminder, what point of concurrency means is simply where the points meet. And so the centroid is where all of the medians meet. Looking at our diagram from the last time, with a few additions, we had the segment AM, and we said AM is a median. Well, now we have a point N, and on either side is congruent, so N would be the midpoint. And we could also say that O is a midpoint of AC. So if we went through here and we drew our other medians, which is going to be BO, hate having BO. We have BO, and then we have CN. And again, I drew this by hand, and so it's going to be slightly off. But what we see is that they all meet in one point. And this point right here is what we would call the centroid. So we can call it, let's call it X right now. And so what we would say then is just that X is the centroid. X is the centroid, and there's only going to be one centroid. In addition to being a centroid and there's only one, you might want to also know what exactly is a centroid. The centroid is the exact center of a triangle. What does that mean? Is that a triangle will balance at that point. That's kind of a silly way of saying it, but if we were to actually hold this triangle, if we were to hold triangle ABC and put it on a finger, if you put your finger on X, this triangle will stay centered on your finger, will not fall over. That is what a centroid is. It's the exact center of a triangle. So of course we have some theorems that deal with the centroid. Centroid theorem, theorem 5-3-1, says that the centroid of a triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. Okay, so what does that all mean? Looking at an example, I see a triangle ABC, and I see a bunch of lines intersecting into a point J. We got to determine what type of point J is. So what I see is that I have, let's look at down here, BC. I have two congruent segments with a point in the middle, meaning Y is the midpoint. So we have a segment, AY, that goes through the midpoint and through a vertex. And we go along and we see the same thing could be said for, we have two congruent sides, Z must be a midpoint, so we have a segment CZ, and then you have BX. So what we could say is that J is All right, we've got a triangle here, triangle JKL, and in triangle JKL, the length of ZW is equal to 7. Where's the ZW is equal to 7, KX, or LX, is equal to 8.1. So we want to find KW, we want to find the total length of this huge segment, and we want to find LZ. All right, so let's start off with part A. Starting off with part A, we want to find the length of KW. It's important to note, and obviously we're in this section, but how do we know how to do it to begin with? Notice we have a bunch of midpoints in here. We have X, Y, Z, bunch of midpoints. So therefore this Z has to be the centroid. So we're going to use our centroid theorem here. Okay, what does the centroid theorem tell us? The centroid tells us, and again we're dealing with KW, so I'm not talking about the other segments, but what the centroid theorem tells us is that KZ is equal to 2/3 of KW. The length to the centroid is 2/3 of the total length. Okay. Now this problem should be noted that you're going to take a couple steps here because we're looking for the total distance. We're not looking for the centroid. We know the centroid length. Or I'm sorry, we don't. We don't know the centroid length. We know something else. So there's a couple steps here to go through. So before I actually jump into it, why don't we talk about what is KW? KW, and this is using that segment additive postulate from before, we could say KW, this whole thing, you can add up two segments to get to that big guy. Add up KZ, and then add up ZW. So the big guy is KZ plus ZW. So let's go ahead and say that. We can say KZ plus ZW. Okay, so now let's do some substitution because we know what KZ is. KZ is 2/3 of KW. So using our substitution, we're really just doing algebra now. KW is equal to 2/3 of KW plus ZW. Those looks like twos, so let's add our line in there. Okay. Now I see KWs on both sides. I see 2/3 KW and I see a KW over here. So it's almost like an invisible 1 here. It's like 1 times KW is equal to 2/3 KW plus ZW. Let's subtract our KWs over. Subtract 2/3 KW, subtract 2/3 KW. And so what do we get? What is 1 minus 2/3? 1 is the same as 3 over 3. So this is the same as 1/3 KW is equal to ZW. Don't we know what ZW is? ZW is 7. So let's put in 7 here. 1/3 KW is equal to 7. Now we are searching for KW. So KW is equal to, how do we get that by itself? Right now we do the opposite. We have 1/3 times KW. So we want to multiply this by 3. Multiply it by 3. 7 times 3 is 21. And thus the length of KW is 21. This is your answer. So some of these will require a lot of work, more so than the example from before. But just be methodical about it and take step by step. Let's go ahead and look at part B now. Part B says we want to find the length of LZ. Okay, so LZ would be here, and this is part of the big sum of LX. So again, using our centroid theorem, we know that LZ, the length from a vertex to the centroid, that is equal to 2/3 of the total length. So 2/3 of LX. Well, don't we know what LX is? LX is 8.1. So LZ is equal to 2/3 times 8.1. We're looking for LZ, so we don't need to do anything more. Well, let's just multiply and simplify. So let's go ahead and type that into our calculator. We type into our calculator, and we should get 5.4. And thus we are done. This one is obviously much simpler than part A, but know how to do both of them and understand the key differences of why they are easier or harder. We've got one final example here. What we want to do is find the centroid of triangle ABC. Triangle ABC. So we have a triangle here, but now it's in a coordinate plane. So we have specific points. So we want to find the centroid. So first it might be helpful to list where our points are at. A is at the point, let's see, we start at 0 and we go over 1, 2, comma 1. We go over 2 and we go up 1. So A is at the point 2, 1. How about B? B is at the point negative 1, negative 2, negative 3, 1, 2, 3, 4, 5. Negative 3, comma 5. Now how about point C? C is at negative 1, negative 2, negative 1, negative 2, negative 3. So negative 1, negative 2, negative 3. I believe that is right. Negative 2, negative 3. Okay. So we have our 3 points. Now let's start talking. What is the centroid, if we remember? The centroid is, in short, yeah, it's where all these things, where all these midpoints intersect, but a centroid is the exact middle. And in fact, that might help us remember how to do this, because there's a shortcut that we could take. We could find where all these actual midpoints are, but we don't want to do that. That's a terrible idea. What we're going to do instead is use the idea of exact middle. Because it's the exact middle, all we have to do is we need to average. We need to find the middle, the x's, and we need to average the y's. We're finding the average x, the average y, the middle x, the middle y. So let's talk about the x's. Talk about 2. If you remember, you find the average. You add up all the numbers and divide by how many you added. So 2 plus negative 3 plus negative 2. 2 plus negative 3 plus negative 2. And how many things did we add? 3, so you divide by 3. If we add this up, we get 2, that's going to be 0, negative 3. That's going to be negative 1. You can do that in your calculator, but you see it's negative 1. So then you do y's now. You do 1 plus 5 plus negative 3. 1 plus 5 plus negative 3. And then we still divide by 3. What does this give us? 1 plus 5 is 6. Minus 3 is going to be 3. Divided by 1 is going to be 1. That was coincidental, but we have the point negative 1, 1. This is our centroid. Negative 1, comma 1 is our centroid. So it's a nice shortcut, different type of problem, but altogether not too crazy, as long as you remember you're looking for the middle of the x's and the middle of the y's.